You've probably seen an X-ray machine, right? At the dentist and a hospital, they're everywhere. But have you ever stopped to think about the insane amount of energy it takes to create that image? And maybe more importantly, where does all that energy actually go? Well, today we're diving into the incredible hidden engineering that keeps these machines from literally melting down.
Okay, let's just get right to the most mind-blowing fact of all. When an X-ray tube fires, a tiny fraction of the electrical energy, we're talking just 1%, is actually converted into useful X-rays. So what about the other 99%? It becomes a massive, focused burst of pure raw heat. This isn't some small inefficiency. This is the entire ballgame. And that is what engineers call the 99% problem. Seriously, managing this colossal amount of heat isn't just some side project in X-ray design. It is the single biggest challenge. It dictates pretty much everything: the power, the size, and the lifespan of every single machine out there. So what happens if you don't manage that heat? The consequences are, well, they're extreme. The little part inside where the X-rays are actually created, it's called the tungsten target, would be vaporized in a single use. The machine would literally destroy itself from the inside out. All right, so let's trace this whole system, starting right at ground zero. To really get how an X-ray machine stays cool, we have to start where that fire is born, the anode. You can think of this component as the first line of defense, engineered to take that initial punch and contain the inferno. Now, early and lower power machines, like the kinds you'd find at the dentist, use what's called a stationary anode. The heat just hits one spot and then gets pulled away into a big block of copper. But for the heavy-duty stuff, that is just not going to cut it. The solution? A truly brilliant innovation, the rotating anode. This thing spins at insane speeds. We're talking up to 10,000 RPM. So the beam of electrons hits a constantly moving target. It spreads that intense heat over a much bigger area, and that's what prevents a total meltdown. So really, the whole anode is basically designed as a heat sink. Its entire purpose is to absorb that initial thermal shock before it has a chance to go anywhere else. Whether it's spinning or standing still, its number one job is to take the hit. Okay, so the anode has absorbed that initial blast, but now all that heat is trapped. The next problem is getting it out. So let's follow the heat on the first step of its escape route, a journey through a very special kind of oil. The whole X-ray tube assembly is literally bathed in something called dielectric oil, and this stuff is a fantastic piece of multi-purpose engineering. First, it's an amazing electrical insulator, which stops the system's high voltage from irking and zapping itself. But second, and just as important, it's a thermal conductor. It actually pulls heat off the hot glass of the tube and starts moving it away toward the outside. All that hot oil is held inside the protective housing. And this thing is way more than just a simple case. Of course, it's lead-lined to stop any stray radiation, but it also has a really cool feature: an expansion bellows. You see, as the oil heats up, it expands, and this bellows acts like a lung, flexing to prevent a dangerous pressure buildup that could literally rupture the entire unit. So if we recap the heat's journey so far, it's really a three-step dance. First, the superhot anode radiates that energy out as infrared waves. Second, heat conducts right through the metal stem of the anode itself. And third, the oil circulates through convection, carrying the heat away from the tube and toward the outer housing. Okay, so at this point, we've successfully moved the heat from a microscopic point on the anode to the entire outer casing of the machine. But here's the thing: containing it is only half the battle. Now we actually have to get rid of it completely. For a simple dental X-ray that's used every now and then, just letting the heat passively radiate off the housing into the air is fine. It works. But for machines that are used over and over again, like CT scanners, no way. That's way too slow. The machine would overheat in no time. These powerful systems need active cooling. And this chart really shows you the ladder of cooling power. You can see the clear progression, right? You've got simple passive cooling for small, portable units. Then you add fans for a standard hospital radiography room. For the really powerful CT scanners, they actually use pumps to circulate the oil through an external radiator, kind of like in your car's engine. And for the most demanding machines, say in a cardiac cath lab, they use a water-cooled heat exchanger for the absolute maximum cooling power. So why does all of this incredibly complex engineering really matter? Well, it's simple. Better cooling means the machine can be used more often, for longer, more detailed scans, and it'll last for years longer. It has a direct, real-world impact on how many patients can be seen and the quality of care they get.
This right here, this is the operator's rulebook. It's the anode cooling curve. It shows exactly how many heat units have built up in the system and precisely how long it's going to take for them to go away. And following this curve, it's absolutely mandatory. It tells the radiographer exactly how long they need to wait between scans to prevent that heat from building up and causing permanent damage. And keeping this delicate thermal system in balance is an ongoing job. Operators have to run warm-up procedures to avoid cracking the anode with thermal shock. It's just like putting a cold glass dish straight into a blazing hot oven. They're constantly optimizing settings, inspecting for tiny oil leaks, and keeping the cooling fans clean. Every single step is about protecting that critical pathway for heat to escape. So the next time you see an X-ray machine, just remember the incredible, invisible war against heat that's happening inside. The 99% problem is this perfect example of elegant engineering that takes a potentially destructive force and turns it into a life-saving tool. And it makes you wonder, doesn't it? What other invisible systems are working all around us, quietly turning chaos into order every single day?